Hello, everyone. Hope this is the end of the day. So it has been a long day for everybody and for me as well. So my name is Aditya and I work at Meta. I'm from India and basically today I'm going to talk about, I will be challenging a core assumption about securing AI systems. Uh, I'll be, sh- I'll be I'll basically show how multi-agent swarms, the new enterprise standard, introduces a novel attack surface. So this stack, uh, it demonstrates how to bypass the air gap and with basically the traditional, not with the traditional exploits, but through something called as policy compliant harm. So we are already seeing multi-agent swarms deployed in critical high-stakes environment, and these aren't future concepts; they are operational realities. For example, Anduril Lattice, for instance, coordinates unmanned systems for border security, fusing intelligence across domains, and this system relies on inter-agent trust to task assets. Similarly, in military applications for Israel, projects like Lavender and Gospel demonstrate multi-agent AI targeting pipelines. These systems use coordinated agents for surveillance, target, identification, and strike recommendations. So in the public sector, China's Sharp Eye Eyes network integrates hundreds of millions of cameras into a distributed swarm. Facial recognition, behavior analysis, and anomaly detection agents constantly communicate and update central ledgers. Even air-gapped clouds, like for example, Singapore's 2025 deployment, are now relying on multi-agent communication for highly privileged, isolated networks. So these examples highlight that the reliance on inter-agent trust is already pervasive, making these systems vulnerable to the architectural attacks that we will going to be discussing today. So let's dive deep into the core assumption that we're exploring today. We directly challenge a core assumption that many of you likely hold about your multi-agent AI deployments, and that is basically that enterprise AI has rapidly shifted from isolated chatbots to complex distributed multi-agent swarms today. Yet, our security architectures, often lag and treating each agent as a standalone application protected by perimeter defenses. The critical and basically the ultimately flawed trust model that we are exploring today is the belief that an air-gapped action agent is inherently safe. But that is not true. And that isn't a model vulnerability. It is an architectural vulnerability in how we compose these distributed cognitive systems. We are no longer defending chatbots. We are defending distributed cognitive systems. So what does this new enterprise type of standard look like? So building on that flawed assumption, if we take a look at the multi-agent architecture that is today, one of the things that comes is that you will typically see is that there is an research agent, often web-facing, feeding into an analysis agent, which then passes information to a highly privileged air-gapped action agent. So action agent is the one that is air-gapped. So each of these agents, operates with distinct privilege scope and its own NHI, which is the non-human identity, is completed with provisioned, API credentials, inter-agent communication. The crucial link here, occurs over, trusted internal channels like gRPC or REST. So if we take a look at this architecture, it mirrors the traditional network segmentation, which most of you would be familiar. And with the research agent in the DMZ and action agent, in the secure enclave, it is pretty similar to what we have seen earlier. And the critical detail here is this: that the agents communicate via structured data like JSON summaries, and this communication is implicitly, trusted because it originates from an internal peer. Just like how we humans trust each other, the agents have their own trust. That trust boundary is something that is exploited as a way to attack this interface. So this implicit trust is, precisely what we will be exploiting. But first, we need to reframe how, we think about prompt injection. And so, moving from the architectural overview, we need to fundamentally reframe our understanding of prompt injection in this multi-agent context. And that's when we, kind of introduce this is what is called as a policy compliant harm, or the PCH. So in single agent systems, the prompt injection is often dismissed as an input, as an input, and and the prompt injection is often dismissed as an input sanitization failure, and analogous to, this is analogous to simple XSS vulnerability. But in multi-agent systems, prompt injection transforms into a powerful lateral movement vector, directly analogous to, techniques found in like Mitre, attack, MITRE attack, TA008. So the promptware kill chain, shown here illustrates this progression: the initial access, privilege escalation, persistence, and lateral movement. Oh, a bit of the slide is like hidden, but that's fine. So, the conceptual reframe is critical, that agent-to-agent communication is in, essence in lateral movement, and the poison context object, traveling from one agent, to another is functionally identical to credential relay between, compromised hosts. So, this brings us to our first class of to the main idea of, policy compliant harm. So this is an attack class where, every individual agent action is authorized and yet is policy valid, and yet the composite workflow, ultimately executes a destructive outcome, because there is no fundamentally malware, no traditional, exploits, no indicators of compromise, yet, every log entry appears to be green, like a sea of green problems, but eventually the attack, exists solely in the semantic composition of the workflow, rendering it invisible to the traditional security operations, telemetry. So if every API call in your SIEM, which is a security information and event management, is authorized, basically how do you detect the attack? So this is the central unsolved problem that we're going to address today. Now let us break down the phases of this attack. And if we go back to the previous slide, which is the phase one, so how does it actually unfold? So the attack is, isn't a single event. It is a carefully orchestrated multi-phase chain that exploits the inherent trust in multi-agent architectures. So basically in phase one, what we have is basically in phase two, which is the payload laundering and summarization, it is the critical innovation over here. And the research agent isn't like compromised in the traditional sense, but what happens here is that it is simply performing its design function of summarizing web content. And I'll be showing in the upcoming slides as to how this payload laundering is used to inject poison context into an air gap node. So the payload, what it does is that it survives this summarization because the LLMs preserve the semantic meaning during compression, and the action agent then has no reason to distrust the summary because it came from an authorized internal peer over a trusted channel. So this is precisely why the air gap fails. And if you take a take a look at the initial phase, the phase one was about getting the initial payload past the external defenses and into a format legible to an LLM, for example, like a JSON object. And this is not theoretical. Several delivery techniques have been documented so far. So, for example, if we take over here that like for example, so for example, if we take a look at the delivery methods, so the key insight here is that these payloads are meticulously engineered to evade both human reviewers and static security scanners. but they remain perfectly legible to the LLMs that can process raw text content. So what we are seeing is a sophisticated visual concealment methods like zero font, sizing, CSS display none, alongside advanced obfuscation, techniques such as XML, SVG, encapsulation, HTML, attribute cloaking. All these are techniques are used for kind of obfuscating data. So the attackers, what they're doing is that they are also leveraging various encoding schemes, including like base 64 and nested multipass encoding to further obscure, their malicious intent. This level of sophistication is, what it does is that it highlights that attackers are actively iterating over IDPI tradecraft, as evidenced by a real-world ad review bypass, cases from late 2025. And in the phase 4, what happens is that we have the action agent that receives the language, that laundered payload as part of its normal operational context. And basically what happens is that the SOC telemetry over here, it shows that we have an authorized agent, we have an authorized API call, we have an authorized endpoint, but eventually what happens is that you get a success, but what happens is that the semantically a poisoned command gets executed in the action node. So now let's examine how a carefully crafted payload gets laundered. So like for example, this is the core mechanism of the attack. So basically, like this is the core mechanism of attack, and what it does is that we have like for example, LLMs are designed to preserve semantic intent. And what research agent does is that it is performing its legitimate function of scraping a poisoned web page, and that basically injects a command into the structured output, and the laundered payload then appears as a perfectly legitimate JSON object that basically goes into the action agent. So basically what happens is that any input filters on the action agent will see clean, well-formed internal data, completely devoid of traditional injection signatures. So what happens is that the malicious intent is semantically communicated, and this is analogous to like money laundering, wherein illicit funds pass through a legitimate business and emerge clean. With the payload laundered, we can now see how it traverses the air gap, and this is where the air gap protects against the direct external access, but it offers like no protection against trusted internal peers. Agent-to-agent communication authenticated via services like mesh, MTLS provides the legitimate channels for the laundered payload to ride. So basically, like what we see over here is that the zero trust frameworks, while robust for identity, fail because the non-human identity of the research agent is indeed authorized to communicate with the action agent. So the critical point here is that the trust boundary is semantic and not network level, and no current framework effectively enforces this semantic trust. So what happens is that the payload traverses the boundary because the boundary only checks identity and not the malicious intent embedded within the communication. So finally, let's take a look at how a laundered payload leads to execution. So what happens is that the laundered payload successfully traverses the air gap, and we have an external network. We have a research agent that is running on Raspberry Pi 5, and what it is doing is that it is scraping a poisoned web page, and that basically translates into a JSON payload, and that JSON JSON payload basically is being inserted into the air gap, wherein like the identity verification is happening, the auth validation is happening, the TLS we have the TLS authentication, and but the semantic intent is not checked. And because of which, what we see over here is that it is passing all checks, and the intent or the command, unsecurely passes on to the action agent, which is like, which is like kind of simulated using like a Jetson platform. So basically, like what we see is that this is a sea of green problem where the attack hides in the noise normal, authorized operations. Next we can see that what we can do, that what this conceptual attack chain can be simulated in a real world. So Uh, the slide that you see over here was something that I was planning to demonstrate today, but unfortunately, because I blew up my Raspberry Pi yesterday while I was trying to connect and try the demo, so I could not bring it here. But like what I did was that I built a 3-device distributed edge lab to physically separate these 3 cognitive nodes, and this setup basically demonstrates that lateral movement is undeniable and not just a software bug. The Raspberry Pi, in this case, acts like a research agent, and it scrapes the external content. And the NVIDIA Jetson, is an action agent, and it is air-gapped from the internet, and it's just existing on a local switch, and it receives summaries only from the Raspberry Pi. The BeagleBone Black over here, serves as a target in infrastructure, hosting, internal record store with like, couple thousands of, database records. And what we see over here is that the Jetson cannot, directly reach the internet. Yet we will see that, the compromise will come from the trusted internal channel, modeled in the form of Raspberry Pi. So now, so what happens is that the attacker, publishes a blog post in the, in the form of like hidden IDPI payload, and then the Raspberry Pi research agent scrapes that blog, summarizes its content into JSON, and this JSON summary now containing the laundered payload is sent to the Jetson over the local area network. The Jetson action agent then, it processes this summary, it interprets the embedded command, and sends a delete API call to the BeagleBone Black, which is the vulnerability that we are targeting over here. So this is basically the attack execution pipeline. So as you can see over here, we have like a white on white CSS text that some attacker would basically publishes in a blog post, and the research agent would scrape and summarize that into an ingestible schema, and then that summary containing the laundered payload is sent to Jetson over LAN, and basically Jetson processes that and interprets that embedded command and selects a delete API call to the BeagleBone Black, which basically executes that command and records a drop from like 14,000 records to 0. So basically the audit log reads like routine maintenance, but eventually what happens is that a semantically poisonous and dangerous command was executed because of this policy compliant harm mode of attack. So basically, we have to think about that at what point your security center could have caught this. So basically, the answer is nowhere, because no individual's step is anomalous. Next, we break down like why current defenses fail against policy compliant harm. So if we let's break down why we would need to look for input filters on the action agent. And input filters basically on the action agent see perfectly well-formed JSON from the trusted internal source, so no injection pattern is detected. Similarly, if we see that network segmentation and air gaps protect against the direct external access, but they don't protect against the trusted peer. So that is the air gap in the communication. Similarly, the zero trust in the current identity-based form validates who is communicating and not what is being communicated. And finally, the SIEM and the Security Operations Center telemetry that monitors individual events, not the composite workflow semantics. So your entire defensive stack, has a semantic blind spot. Now let us consider the implications for incident responses. What we can do if we are vulnerable to this kind of attack. So even after a breach is discovered, the incident response teams face a forensic void. The traditional DFIR relies on atomic indicators of compromise, but policy compliant harm leaves no such traces. The attack exists only as a semantic pattern across the multiple agent logs, requiring cross-agent workflow reconstruction. This means that this basically means that, the current DeFi playbooks have no policy or procedure for the policy compliant, composite harm. So, like for example, if we take a look at what are the different defensive architectures against this. So what we can do is that we can have as a first line of defense, we can have a cryptographic agent to agent attestation. And the key here is that signing the content and not just the sender's identity. Each agent in the chain must, cryptographically attest that I received data from source X and applied transformation Y, and the resulting output has a semantic property Z. So that semantic translation and cryptographic attestation is very crucial in kind of like securing. The receiving agent, then what it does is that it verifies the full provenance chain, and if the research agent's attestation says, okay, summarized external web content, but the payload contains an execution command, the attestation fails the semantic validation. So this basically is similar to like what we have seen in software engineering, and this looks like code signing, but for inter-agent context objects. So next we'll explore how execution phase sandboxing and semantic firewalls are useful. So basically, building on the cryptographic attestation, we have now building on the cryptographic attestation, we now introduce like semantic firewalls and execution phase sandboxing, and these are crucial for validating the intent of the data and not just the format. A semantic firewall, firewall acts as a new layer, inspecting the actual meaning of inter-agent communication. What it does is that it ensures that the message aligns with the agent's defined purpose. We also advocate for a dual LLM pattern, which is basically used, for example, in Google's Llama 4, and like for example, what it does is that it separates the reasoning engine from the execution engine, and this prevents basically a single point of compromise. And finally, the execution phase sandboxing provides a critical last line of defense. What it does is that it validates agent outputs against an allowed action schema before any destructive action. So these measures, when we combine with attestation, build a robust defense. But even with these in place, we still need better visibility. And while the previous defenses prevent malicious execution, we also need to enhance our detection capabilities. So current SIEM, are largely stateless and correlating, and what they miss is the broader multi-agent workflow. So we need to shift to a sequence-aware SOC telemetry, and that basically means that what we can do is that we have to have an agent workflow graphs. These define and track the expected flow of data and actions through our agent. But modeling these workflows, we detect semantic anomalies. For example, an external summary, triggering like a kind of a attack vector. So far in this talk, what you have done is that we have seen that a single model, like for example, a web scraping or a text-based poison injection, and what issues can it cause. And what we see is that in the first class of the non-text modal injection, where there is image-based semantic injection. And in that, we have multiple attack surfaces that we can target. There's steganographic, wherein you have LSB pixel, we have the DCT coefficient, and encoder, decoder on the neural network layer. And again, there is a typographic, injection vectors, wherein you have a fixed step, and text renders as image. That basically all feed into a multimodal LLM, and that basically jailbreaks, and compromised output is rendered at the attack surface. For the audio-based semantics, again, we have like, transcriber muting. We have like dual audio, wherein, for example, you have a benign voice in the foreground and you have a malicious voice which is hidden, and basically model follows the hidden instead of the foreground, voice. And again, in the audio or the audio input side, we have the over-the-air audio jailbreak, physical speakers, model reverbs, frequency loss, and all of these basically, feed into the LLM that kind of like semantically injects a poisoned context into into your action agent or air gap node, similar to like, what we had like seen in the text-based, policy compliant harm models. So in the video, again, in the video-based semantics, we have like, let's imagine a case wherein we have like a 2-minute video consisting of, 24 frames per second. In that, we have like frames 1 to 12, wherein we have benign content that passes screening and it builds trust, and that is basically committed. But what happens is that in interleaved frames, we have like jigsaw payload and like, distributed characters that are injecting, malicious content or malicious intent into the air gapped boundary. And eventually what happens is that all of this malicious intent is injected into a video LLM aggregation, and all of the semantic trust is broken and passed on to the air gap node, and from there it leads to the action agent. So that basically, is basically tells us that our attack surface is not limited to only single mode of attack types. It is there are multiple other modes, such as audio, image, and video that can be used to kind of attack our multi-agentic systems today. So another is basically like for example, if we fuse like multiple modality of data types, and for example we fuse data from like image, from audio and document, which is very common in today's surveillance systems, used by government, used in like in multiple use cases in today's world. And what happens is that this fusion mechanism eventually leads to like an embedding misalignment, metadata poisoning, and eventually what you get is that you end up having an unauthorized command being executed on the side of the action end. So there are what we can do to basically defend against these multimodal systems. So the proposal was that we have like a 3-layer multimodal defense architecture. What we do is that in layer 1, what we do is we sanitize. So for example, we have a multimodal input. So what we can do is that we can see in the sanitization that is there a mismatch detection? Is the spectral analysis correct? Is this what this agent is supposed to expect when it processes the data from each type of modality? And then once that attestation is done, that is, it passes on to layer 2 where the context is isolated, and you have a quarantined LLM that basically processes the tainted data, and what it does is that it filters the output, and then it is only after the output is filtered, it is the privileged LLM is handed over the execution, and then basically the control commands is passed on to the layer 3 where validation happens, and where what happens is that, and for each type of modality or data type, we expect that that is this agent expecting to perform this particular action. Was this action intended? So all of that, for example, is something that is detected or checked in the semantic shift detection, and only when that shift detection is verified, that output is passed on to the execution mode. So basically, what are these implications? What are the implications for enterprise deployment? The attack, it scales infinitely. A single poison web page, can compromise an enterprise swarm that ingests it. But so we have an exponential attack surface. The organizations deploy like more as we see that there are more and more deployments of specialized agents. The number of lateral movement paths multiply, and every time a new agent-to-agent communication is done, that is a potential vector for laundered payloads. So what is the key takeaway? The key takeaway is that we need to map all agent workflows across all modalities. Similarly, the second pattern that we need to identify in our multi-agent workflow is that to understand that the trust models are broken and the fundamental assumption that internal agents are benign is flawed. So identity-based, zero trust like MTLS, NHI is insufficient because, when threat is detected, it is not just identity-based, it is semantic-based and network-based because, across the modalities and all across the communication between the agents, what is preserved is a semantic meaning between the LLMs. So therefore, what should be our action? Our action should be to shift towards semantic trust. So that should be the second design pattern that we need to encode in our multi-agent, action design. And eventually, we need to immediately, review our architecture, and what that requires us to do is that, that enterprise swarms, need to be audited. We should identify all air-gapped and privileged agents that consume summaries or context objects from lower privileged peers. And as a result of this, we will have to enforce semantic boundaries for that. So the key takeaways, there are five key takeaways, from what I talked about today. And topic number one, for example, agent to agent communication is the new lateral movement surface. We need to treat internal traffic with the same security as external. We need to identify that each agent and the semantic it is passing to its peers cannot be trusted. Number two, semantic trust is broken. Identity-based zero trust, MTLS or NHI cannot validate semantic intent. We need to move to content-aware cryptographic attestation. And when I say content-aware, what I mean is semantics needs to be, checked. Number three, payload laundering is real. LLMs compress and launder malicious payloads into clean, policy-compliant JSON, and that bypasses traditional input filters. Number four, air-gap is an illusion. Air-gapped action agents, if we see its deployment in the government, assuming that anything that is air-gapped is safe, that is not true today, because air-gapped action agents can be compromised via trusted internal peers that have access to internet. And network isolation does not equal semantic isolation. And last but not the least, shift to agentic DFIR. What that basically means is that we must reconstruct cross-agent workflows, agent workflow graphs, and not just hunt for atomic IOCs.